In this video, I'd like to have a discussion, but apparently it will be one-sided since it's just me. But this is a comparison I like to think through when we look at different types of transition metals, because once we start learning about transition metals, we're bringing in knowledge from all over our chemistry practice so far. And so I'd like to compare elements like platinum and gold to elements like scandium and manganese. Um, and tell you right off the bat as we compare these that our platinum and gold are going to be less reactive in general as metals, while our scandium and our manganese are much more reactive. And so let's take a look at these and let's compare some of their properties as we go. So for our platinum and our gold, if we just go and look up their redox potentials, let's look up their standard reduction potential for platinum. It's going to be 1 plus 1.20. And the standard reduction potential for gold is going to be 1.5. Some places reported as 1.7, so it's somewhere in between there. And just looking at that right there, those high positive reduction potentials, we can say right off the bat that for both platinum and gold, it is easy to reduce these, which means it is hard to oxidize them to ions. Now, if we compare that to scandium and manganese, we're going to see the opposite. So if we look up the reduction potential for scandium, we're going to get a value of negative 2.09. And our standard reduction potential for our manganese is negative 1.18. So this is the opposite side of the spectrum. These are really easy to oxidize. And so it's easy to remove an electron from these ones. It's easier to become a cation or one of its many different oxidation states. And so it's going to be able, that ease of oxidation will make these much more reactive. And when it's hard to oxidize something into its ionic form, there will be less reactive. And so right there, just those redox potentials of these metals tell us so much about what to expect when we try to combine these with other elements or use them in reactions. And it tells us how we should utilize them as well in the lab. Looking at where these are on the periodic table, we could see that we have our platinum and gold are coming from our 5D block or row. Let's call it a row. So that 6th period, whereas our scandium and manganese are coming from the 3D row or our 4th period of the periodic table. And so this is really our first transition metal row, while our platinum and gold are in our 3rd transition metal row. So these platinum and gold atoms are much bigger. Those valence electrons, those 5D electrons, which aren't valence necessarily, are further away from the nucleus. So they have a smaller effective nuclear charge that they're experiencing because it's that bigger atom. We can also see our scandium and manganese are more than half filled within their d orbitals, while our platinum and gold are less than half filled. And so there's more room to add electrons, I guess you could think of that as well. And so from this information, kind of some of the things I take away is that for our platinum and our gold, there's more shielding that's occurring. It's experiencing a lanthanide contraction. It has the lanthanide series between it and the 5D electrons and the nucleus. And we have less shielding occurring for scandium and manganese. And in general, what we're going to see is that it is going to just cost less energy to remove an electron, considering all these different factors. And the evidence for that is our reduction potentials. And it'll cost more energy to remove an electron from our platinum and gold. And you know, we've tied this before to metallic character too. And so that the ease, that ionization energy, the ease of removing an electron speaks to how metallic a metal actually is. And so we could say those scandium and manganese are behaving in a more metallic way. in that sense. However, platinum and gold being lower on the periodic table does also increase its metallic character too by reducing its electronegativity and its that it would actually have a sign to it as well. And so when we look at these and compare them and compare like these general reactivity trends, there's a lot of different factors that go into it. And I think that's kind of the fun piece about transition metals is that there's lots of little things that are tunable or explorable within the relative reactivity or chemistry of these different elements.